Hello everyone, this is Professor Roman. Let's continue the group theory lectures. We've been talking about direct products, internal direct products, and we talked about cancellation in direct products. Now we would like to generalize the internal direct product from families of just two subgroups to arbitrary non-empty families. Would look like this, of distinct subgroups of a group G. So we'll assume that all these are distinct. The first thing we need is a generalization of the definition of element-wise commutativity, and that generalization is probably just what you would expect. A non-empty family F of subgroups of group G has element-wise commutativity if every pair of distinct subgroups in the family commute element-wise. So if we take two elements from different members of the family, they will commute. Now, as is the case for two-member families, we're going to require that our families F be normal families, meaning that every subgroup in the family is normal. Neither essential disjointness of the family, which would look like this, or even pairwise essential disjointness, which would be stronger than essential disjointness, every pair of members of the family are essentially disjoint. Neither of these is strong enough to guarantee unique representation when we're dealing with arbitrary families. We're going to have to find a stronger version of essential disjointness. And it's not terribly difficult to see this. If we can even see that there's a problem if the family has three subgroups, H, K, and L. This is what pairwise disjointness would look like. Pairwise essential disjointness. Now this will give us element-wise commutativity, but if we want every element of the join, which would be also the set product because the subgroups are normal, to have unique representation as a product, HKL, where little h is in capital H and so on, little k is in capital K, little l in capital L, we can't allow any element, little h in H, for example, to be equal to a product, little k, little l, coming from the other two subgroups, with the obvious exception of writing 1 equals 1 times 1. The identity is in all these subgroups, so this will always happen. But except for this case, an equation of the form H equals KL, where at least one of these is not the identity, is going to violate unique representation. Another way to say this is that we cannot allow any non-identity element of H to lie in the join or set product of the other two subgroups. So here's what it looks like in symbols. And of course this applies symmetrically to the other subgroups. So these three conditions must hold. Now you might be wondering why I'm not just writing set product here, KL, HL, HK would look simpler and be a little more informative because the normality means these are the same. Well, the reason is when we get to arbitrary families that could be infinite, we don't have, or we have not defined, a set product of infinitely many groups, subgroups. But the join is defined. So to proceed, I want a little notation. This is the join of the entire family with the exception of H sub I. And I'm going to denote that this way, H sub not I. So I'm going to just read this H not I. This symbol, I'll draw a bigger version of it, is a commonly used symbol for logical negation. The other symbol is this one, but I prefer this one because this is a symbol that's used for a lot of other things too, binary relations and so on. So I read this H not I, and it's by definition the join of all the members of the family except H sub I. Now this definition applies to any non-empty family of subgroups. Normality is not an issue here. A non-empty family of subgroups of a group G is strongly essentially disjoint if each H sub I is essentially disjoint from H sub not I, the join of all the other members of the family. Okay. This term, by the way, is my term. So is essentially disjoint. So I don't know if you're going to see these terms anywhere else, but I'm not aware of a standard term for this property. So I call it strongly essentially disjoint. Certainly a strongly essentially disjoint family is pairwise essentially disjoint, but the converse is not true in general, and I'll leave that for you to think about. So we have three levels of essential disjointness. Let me get this other page back. This is just plain essential disjointness. It's the weakest version. Pairwise essential disjointness is stronger than essential disjointness. Just like, by the way, pairwise relatively primeness is stronger than relatively primeness for integers. And then we have this third level, strictly stronger than the previous two, strong essential disjointness. It's also worth noting that any permuting family, regardless of the normality status of its members, is strongly essentially disjoint if no element of any subgroup is a product of elements of the other subgroups, except again for the trivial. One is a product of identity elements. So normal subgroups are permuting, so that they fall under this category. Here is an important tidbit concerning strong essential disjointness that we will use. Let F be a strongly essentially disjoint family of subgroups, then the product, H1 through HM, of non-identity elements of G, each of which belongs to a different member of the family, cannot equal 1. So this equation cannot hold if the HIs are non-identity and come from different members of the family. This is actually a unique representation of the identity element. And the proof is very simple. Since none of the factors is the identity, there has to be at least two factors here. And so if H1 lies in one of the family members, say H sub I, we can throw everything else to the other side of the equal sign. H1 will then not only be an HI, but it'll be in the join of all the other subgroups. And that's trivial. That contradicts H1 is not the identity. Okay, now we can describe the generalization of the internal direct product to arbitrary non-empty families of subgroups. A group G is the internal direct product of a family of subgroups if the subgroups are normal, in other words, the family is normal. G is the join of all family members, and the family is strongly, essentially disjoint. This is a separation property, okay? Very strong separation of the family members. And we'll use the bow tie notation, again, for the internal direct product. This definition, this generalization, has the desired properties: element-wise commutativity and unique representation, at least up to the order of the factors. That's something we can't control. We did control it in a sense when we were talking about the internal direct product of two subgroups H and K, because we always mentioned H first and then K, so we imposed an order on the family. We wrote all our products as little h, little k. But in general, arbitrary families will not have any kind of obvious order applied to them. So we give up complete uniqueness. It's only uniqueness up to the order of the factors, which is not a big deal because the factors commute because they belong to different subgroups. So it doesn't really matter. So this internal direct product has element-wise commutativity and it has unique representation. Any element little a of G can be written in a unique way except for the order of the factors as a product of non-identity elements that belong to distinct members of the family. As for proof, well, since the internal direct product of any pair of family members exists, these are normal, they're essentially disjoint because the whole family is strongly essentially disjoint, then these subgroups commute element-wise, and therefore the whole family commutes element-wise. So that part is straightforward. Unique representation is not difficult, but a little testy. Suppose that we have two products that are equal, and we can assume n is less than or equal to m, and the factors on this left side, h1 through hn, they belong to distinct members of F. They're non-identity factors. And on this side, these also belong to distinct members of the family. But the h's may belong to different members than the k's. Okay. I should say non-identity. Okay. So let's say we have H1 belonging to M1 and so on, K1 belonging to N1 and so on. Now, in this equation, if one side is the identity, if it reduces to the identity, then we know from the previous result that both sides are the identity. So what I didn't say here that I probably should have is none of these are the identity unless this whole thing is just one. Okay, can't stop that. Okay, now we want to show that the h's are equal to the k's, that n is equal to m and each h is a k. Well, the idea is simply to collect factors that belong to the same family member and move everything to one side of the equal sign. So we have an identity. The other side, we can appeal to the previous tidbit. But since the individual subgroups in the family don't have to be abelian, we have to be a little careful. We can't just throw everything on one side and reorder them any way we want, because two members of the same subgroup cannot be, the order cannot be switched. Okay, so here are the details. First, we have to note that some of these family members, M1 through Mn, may be the same as some of these family members, N1 through Nm. But element-wise commutativity implies that we can assume, by reordering the factors on each side separately, we can reorder the h's, we can reorder the k's, so we can arrange it that that M1 is equal to N1 all the way up to, let's say, Mu equals Nu, but that the rest of the M's and the rest of the N's thrown together are distinct. So we want to match up the M's that are equal to N's, move them to the beginning. That much we can do. Okay. And you may need to think about that for a few minutes. Of course, if there are no common family members on the two sides, then U would be 0 here. We don't have to do anything we have to do. Okay, so when we look at this again, if M1 and N1 are the same, if there are any common members on the two sides, M1 and N1 would be the same, M2 and N2 would be the same until we get to a certain point. Mu and Nu would be the same. Then the rest are different on both sides. So let's say at least that U is bigger than or equal to 1. So M1 and N1 are equal. Okay, so H1 and K1 belong to the same family member. Move K1 to the other side. We have K1 inverse H1. This now belongs to M1, or equivalently N1. Suppose that K2 and H2 belong to the same family member. Then it's going to be a different family member than the one that contains H1 and K1. So I can move K2 over here, K2 inverse. It will commute with this because the two factors belong to different family members. So I can move it over here, and we now have this equation. Oops. K3. We continue to do this as long as the family members on both sides, corresponding on both sides, are equal. So we'll end up with an expression that looks like this. We pick this one up at H sub U plus 1 through Hn, and this one also, K sub U plus 1 through Km. Finally, this can be moved to the other side. And so it now looks like this. Here is what I moved over. But now each of these factors, and by factor I mean the stuff in the parentheses or individual members here, belong to distinct members of the family. Now, the previous theorem, 917, implies that there are none of these individual factors. So U is equal to N, which is equal to M, and each one of these in parentheses is the identity, and so H1 equals K1, 2. And now, maybe I should then change these to M or N, but it doesn't really matter. So that is unique representation. It's worth reading this over a couple of times. It took me a couple of times to write it, to be honest with you, because I wanted to make sure there would not be any room for confusion. I hope I did. This is just simple algebra, but it took a while to find a complete explanation, I guess you might say. Okay. The relationship between internal and external direct products continues for larger families. We've already seen that if we have two subgroups of a group G, if their internal product exists, it's isomorphic to the external product. That will apply when G is the internal direct product of any finite number, positive finite number of subgroups. And that's just a matter of iterating, and I'll let you look at that. And from the other perspective, is in a sense even simpler, we form these subgroups of the external direct product where there's an H in one factor and trivial. All the others are trivial. It's exactly what we did for two subgroups. And then the external direct product becomes an internal direct product.